Okay. So let's get started. We have homework 8. Homework 8 to go. So the exam is next Tuesday in class, and we have five problems, 5 regular problems plus 1 bonus problem. So it's in total six problems, 1 hour 20 minutes. So let's take a look at homework 8. 7.3. So determine the Nyquist rate corresponding to each of the following signals. Okay. The first one is pretty simple. It's a sinusoidal signal. So you can plot the spectrum. Okay, so it's 1 plus 2 sinusoidal signals. So xt first one is cosine 2000 pi t. So the frequency is 2000 pi. Second one is sine 4000 pi. And you can plot the spectrum of xt. And the 1 is a constant signal in the time domain. So in the frequency domain, it corresponds to the impulse. And the second one, cosine, is a pair of impulse. And the sine is another pair of impulse. It may look like this. But to determine the Nyquist rate, all you have to do is to figure out the bandwidth. So from this spectrum, you can see the bandwidth is 4000. 4000 pi. So the Nyquist rate is 2 times the bandwidth, which is 8000 pi. $8,000. So for the second one, this is a sync type signal. Xt is sine 4000 pi t, 5 pi t. But you can do 4000 pi here and scale it by 4000. And this is a sync function, scaled by constant. So if you plot the spectrum by the Fourier transform, the transformation of this sync function, the spectrum is a rectangle spectrum. And so the rectangle will span over negative 4000 pi to 4000 pi. So this is the spectrum of this xj, xt. And from here, you can see it still have the same bandwidth, 4000 pi. So the Nyquist rate is 2 times bandwidth, is 8000 pi. Okay, so this is also simple application of the Fourier transform. Now the last one is taking the signal in part B and raise it to the power of 2. Okay, so this is a little bit different. You cannot find such a Fourier transform pair in that table. So so how do you work out the spectrum of this signal? Do you have any ideas? The sinc function raise it to the power of 2. Any comments? And maybe you should think about utilizing some properties of Fourier transform to simplify the calculation. Right. So from part B, we know the Fourier transform of part B. That is clear. Fourier transform of a sinc function, the rectangle. So now we need to deal with a sinc function to the power of 2, which can be viewed as a product, right, of product with itself. So it's a product of 2 sinc functions. Okay, this is the same. And then if we take the Fourier transform on both sides, so the Fourier transform of a product of 2 signals, we have property of Fourier transform saying that the Fourier transform of a product of 2 signals equals taking the Fourier transform of each signal and then perform a convolution between them. That's the multiplication property. So what you do, you don't even need to do calculations here. All you have to know is that if you apply Fourier transform here, then in the frequency domain, you are going to do the convolution between these 2 spectrums. Okay? The convolution happens in the frequency domain. So for each of this spectrum, we know from part B that this is a rectangle spectrum. Okay. So we have 2 such rectangles. Okay, we have 2 such rectangles in the frequency domain. And then we're going to take convolution between them. Okay. So this is like you have 2 signals. It's the same thing as if you have 2 signals, as if you have 2 rectangle signals and you perform convolution in the time domain. You can view this as signals in the frequency domain. So okay, it's basically a convolution between 2 rectangle functions. And you can tell, well, and this is a basic fundamental problem about convolution, right? We have done this in the convolution lecture. If you take convolution between 2 rectangles, you get a triangular signal. But so the idea is that you fix one of them, and for the other one, you do a time reversal, which is again a rectangle because it's symmetric, and then you move it from left to right. And the convolution is basically their overlapping area, and you can see that at the beginning their overlapping area is increasing because they are. Once we move this rectangle from left to right, okay, the overlapping area starts to increase. At some time, they perfectly overlap with each other while you reach this maximum point. And after that, if you keep moving to the right, the overlapping area starts to decrease. So the convolution is such a triangle. So this is the xj omega. And because of the convolution property, the width of this triangle is actually 2 times the bandwidth of this rectangle. So this is 8,000 pi and negative 8,000 pi. But if you start okay, so you are moving this one from left to right, and you can see that they start to have overlap when this is 8,000 pi. Okay, they start to touch each other at this point, and at this moment, this one is negative 8,000 pi. So that this triangle spans over negative 8,000 to 8,000. Okay, so this is the spectrum of this signal, part C. So once you have that, you just the Nyquist rate is 2 times the bandwidth is, so it's 16,000 pi. Okay. Question?
Because so it goes from negative 4,000 pi to 4,000 pi, which is total 8,000 pi. So wouldn't it start crossing over at negative 12,000 pi?
Negative. But if you fix this one, right, and you move, you only shift this rectangle, they start to touch each other when this one is located, the right ending point of this rectangle is located at negative 4,000.
And it's 8,000.
Okay.
And so it's 8,000 y. So shouldn't it extend to 12? So 4 minus 8. So it's negative 12,000.
That's a good question. Maybe there's okay. Let me think about this. Yeah, 4,000 is okay. I think this figure is this is illustration maybe incorrect. So let's actually refer to the convolution definition. So let me call this V omega. So xj omega, I'll just write omega instead of j omega. It's the convolution between V omega and so basically we have a property saying that if you take convolution of 2 signals, then the resulting convolution, the resulting signal, the length of the resulting signal equals the length, the sum of the lengths of the 2 signals. So this one has 8,000 duration in frequency, and it spans over 8,000 pi. This one spans over 8,000 pi. So in the end, the resulting convolution signal will span over 16,000. But why is this true? I think if you write down the definition of convolution, so it's V tau times V omega minus tau d tau. And what happens is that now we know each V omega is constrained within a certain bandwidth. So V omega equals to V omega times Okay, let me just try to simplify that. So we know that each of the signal V omega is constrained within a certain bandwidth. So here the integration, by definition, the integration starts from negative infinity to positive infinity. But since V omega is actually band limited, so we can restrict, we can restrict the integration over their domains. So for this one, for V tau, we know that tau must be restricted between 4,000 pi and negative 4,000 pi. So, right, this V tau, this omega is restricted between this 4,000 and 4,000. And for this one, we need to have omega minus tau be restricted between 4,000 pi and negative 4,000. So and think about it. And then we will have a constraint on tau. So the tau here, this is one constraint. The other constraint gives tau is between tau less than equal to omega plus 4,000 pi, and this one's tau is greater than omega minus 4,000 pi. Okay. Therefore, this integration can be restricted. This integration can be restricted. Now the one is between negative 4,000 pi and 4,000 pi. And the other, we actually have gone through this when we talk about the convolution in the lecture 3 or lecture 4. The other interval for tau is between omega plus 4,000 and this is omega minus 4,000 to omega plus 4,000. And you can visualize the intersection of these two intervals. It is possible that they may have empty intersection, and in that case, the integration will become 0. So we are only interested in the case where these two intersections have non-empty. These two intersections have non-empty intersections. So first interval is a fixed interval, 4,000 to 4,000. The next interval is taking this interval shifted by omega. Okay, shifted by omega. So this is like omega. So this will be omega plus negative 4,000 pi. This is omega plus 4,000 pi. So whenever these two intervals have a non-empty intersection, that implies this integration is not meaningless. then you will have something for the signal. So the signal will not be 0. Otherwise, if these two integrations does not intersect with each other, then the integration will be 0, which means the convolution signal will become 0. Okay. And then you can see that the value of omega such that these two intervals has non-empty intersection is when omega is between negative 8,000 pi to 8,000 pi. Great. Wait, let me think about this. 4,000. Yeah, if this is negative 8,000, then it's negative 12,000 pi. Yes, so when omega takes value of negative 8,000, then the left ending point is negative 12,000. And right ending point is 4,000 minus 8,000, negative 4,000 pi. So the right end point will touch the left end point of this interval. So that's the boundary case. And when omega equals to 8,000, then this left ending point will touch the right ending point. That is another boundary case. So basically, when omega is within this range, this x omega, this convolution signal will have non-empty response. So you get this. So that's why this triangle spans over negative 8,000 to 8,000. But to summarize, the rule is that the length of the convolution signal is basically equals to the sum of the lengths of these two individual signals. Okay, so this one has 8,000 lengths, this one has 8,000. So the sum together gives 16,000. This also applies to the discrete convolution. So basically, when you convolve two signals together, they will generate a longer signal that equals to the sum of the lengths of the two individual signals. So this actually implies that, if you take a signal and raise it to the power of 2, this operation will increase the bandwidth of the signal, right? Because when you raise it to the power of 2, you are like doing convolution in the frequency domain, and the convolution will expand the spectrum of the signal. So you can see the resulting signal has a wider spectrum. So let me remove.
Sorry, do you think, will that be true for other signals or just the sync signal that it'll do that?
Sorry, can you repeat the question?
I was wondering if other types of signals will follow the same pattern if they're squared, or if it just does it with this situation because it's a sync signal.
Well, I think they will follow the same type of convolution behavior in the spectrum domain. So if you take any other signal, any other general signal, like the signal in part A, and raise it to the power of 2, when you raise it to the power of 2, you are doing multiplication in the time domain. And then by the multiplication property of the Fourier transform, this is equivalent to doing a convolution in the frequency domain. Okay.
Mhm.
In the frequency domain, you always perform convolution. You take the spectrum, you take two spectrums, take convolution with each other. But for this part C, for this specific example, the spectrum happened to be for each of these signals, the spectrum happened to be a rectangle spectrum. So two rectangles taking convolution gives this special triangular spectrum. But of course, if you take the part A as an example and raise it to power 2, then you are going to convolution. You are going to perform convolution between two such spectrums, and then the resulting spectrum will look different. However, the bandwidth still follows the same rule. The resulting bandwidth after convolution equals to the sum of the bandwidth of the two signals before convolution.
Okay, that makes sense. Thank you.
So that part follows the same property due to convolution. And this is this example, makes, because the spectrum is rectangle, so it makes it easier for us to calculate or visualize this convolution. But let's say if the signal has, okay, if this base signal turns out to have any arbitrary spectrum, like this one, and we know it's band limited, so we consider raising it to the power of 2. Then for this signal, the resulting spectrum would be taking this, copy this spectrum and convolution with itself. Now, after the convolution, you don't need to care about the specific convolution result. All you have to know is that after convolution, by the convolution property, the resulting spectrum will span over. In this case, it's 2 times the bandwidth. So I don't know maybe this is the resulting convolution, but in any case, they will always, the length of the resulting convolution is equals to the sum of these two. So this will give us a 2 times bigger bandwidth. Yeah. So the conclusion is the same. And no matter what you put inside, for any signal, if you raise it to the power 2, then for the resulting signal, the Nyquist rate will be increased by 2 times. Because now the bandwidth is 2b, so the Nyquist rate is actually 2 times the current bandwidth. It's 4 times your bandwidth. And 4 times bandwidth is 2 times the previous Nyquist rate for the original signal. Yeah. So but basically, when you raise the signal to the power of 2, the Nyquist rate will always be increased by 2. Yeah. And you can also consider raising it to the higher power. For example, if you raise it to power 3, then that is like further multiplying this signal by itself, okay, by another sync signal. And then you can apply one more step of the multiplication property of the Fourier transform. So that would corresponds to, well, taking the spectrum of this signal, or taking this spectrum and convolution with another spectrum of the original signal. Okay, now this spectrum has bandwidth 2b, and this spectrum has bandwidth b. when you take convolution, the resulting spectrum will have bandwidth 3b, okay, because they will be adding, the length will be added up. So if you raise it to the power of 3, then the Nyquist rate will be increased by 3 times. Okay, so this is how we deal with such type of operations. Okay, now, this is a nonlinear operation. We take a signal, raise it to the power of 2. So 7.4 is the same thing. We need to determine, given that xt has a Nyquist rate omega naught, determine the Nyquist rate for the following signals. Because the Nyquist rate is only related to the bandwidth, so all you have to consider is the bandwidth of these signals. So A, B, C, D, these signals are generated by the original signal xt by following certain operations. So you need to discuss how these operations affect the bandwidth of the spectrum. So part A is basically a linear combination. This is like a linear system. Okay, this is the original signal. This is the original signal with a certain time shift. So all these are basic operations. So if you think about Fourier transform of this signal, this is the original spectrum, and for this one, by the time shifting property, you will have a original spectrum multiplied by a certain phase shift. So once you do Fourier transform, you have this is EJ omega t this is EJ omega t time shift 1. And this is by the time shifting property. Positive. I think it's positive. Like the time shifting property. Let's check. Yeah, sometimes I also get confused of these basic properties. Oh yes, yeah, it's negative. Yeah. But you can see that neither of these operations would affect the bandwidth. So in fact, what happens is that it's like multiplying the original spectrum by a certain complex coefficient. So it's just a scaling of the original spectrum in the magnitude part. Okay? So the bandwidth will be the same, will remain the same. So in this case, the Nyquist rate is the same.
How do you know the bandwidth will remain the same?
Well, this is the resulting spectrum, right? It's the original spectrum multiplied by a certain a fixed complex number. So it's like, okay, if the original spectrum looks like this, so the resulting spectrum will be taking this spectrum multiplied by scaled by another function, but it will not affect the bandwidth, because whenever the original bandwidth is okay, but if you consider this point outside the bandwidth of the original spectrum, then at this point the original spectrum will be 0. 0 times any numbers still gives you 0. So the bandwidth So the bandwidth will remain the same, but the shape of the spectrum may change due to this scaling factor.
Okay.
Yeah, because the original spectrum is band limited. And here we only care about the bandwidth. So part B is the same thing. This is a differentiation of the original signal. So you apply the differentiation property of Fourier transform. And well, you see that this differentiation only scales the spectrum by a certain function j omega. So again, it does not affect the bandwidth of the spectrum. So for this one, so for part B, you have the same Nyquist rate, omega naught. For part C, now it's clear from the 7.3, it's xt raised to the power of 2. So this is a convolution in the frequency domain. So the bandwidth will be increased by 2, by a factor of 2. And then you can discuss the Nyquist rate. So in this case, the bandwidth will be expanded. This is part C. Now part D is a modulation where you modulate the signal by cosine omega naught t. And we have discussed before in the Fourier transform part. Well, cosine, this modulation is basically shifting the spectrum of xt to a higher frequency. So I think we can just refer to this lecture. Don't have it here. Yes, right here. Okay, so once you modulate by cosine omega naught t, the resulting spectrum is taking the original spectrum, shift one copy to the left by omega naught, and another copy to the right by omega naught. Okay, so now we can discuss this. So you have an xt with Nyquist rate omega naught, which means your original spectrum. Okay, I'm gonna just show. Is omega naught over 2 and negative omega naught over 2. Okay. Looks like this. But this is the bandwidth, so the Nyquist rate is 2 times the bandwidth, which is omega naught. And now, after modulation, we are shifting. Okay, by this property, we are shifting one copy to the left, another to the right by omega naught respectively. So this one will become negative 1/2 times omega naught, and this one's negative 3/2. So this is the resulting spectrum. And then you can talk about the bandwidth of this spectrum. Okay, it is clear from the picture. Once you have the bandwidth, you multiply it by 2, you can have the Nyquist rate. Okay, any questions? We have one more 7.9. Okay, again, we have this sync signal raised to power 2, right? So we know how to deal with this one. We have such a signal xt, and we want to sample with a sampling frequency omega s at 150 pi. And the resulting sample signal is called GT, and the corresponding Fourier transform is called capital G. Now determine the maximum value of omega naught such that the G spectrum equals to 75 times the X spectrum for omega between negative omega naught and omega naught. Okay, so basically you need to find out a band, frequency band, such that this equation holds. Okay. Well, the idea, since we have the signal, we have X, so we can plot plot is spectrum capital X. Now we know the sampling rate, so we can plot the spectrum capital G. Once we have these two plots, we can tell from the picture when will this equation hold, right? So these two can be plotted. So let's just plot them out. And because this equation has a very specific coefficient 75, so when we plot these spectrums, we need to pay attention to the magnitude scaling. So let's do this one by one. So xt okay, so from the previous discussion, we know that this signal has a spectrum. So it's a rectangle type signal. Spectrum is given by 50 pi and negative 50 pi. Right, so this is a standard transformation pair. So this is spectrum. And then xt raised to the power of 2. So we are going to do convolution between two such rectangles. So the xt, now taking Fourier transform. Okay, now you take convolution, you will have a rectangle signal. And the bandwidth is 100 pi. Okay, so this is the spectrum of xt. But at this, let me think about this. At this time, so let's just denote the amplitude as capital A at this point. But if you look into the table, you can find specific values for the magnitudes of this spectrum. You can either use the specific values, or here I'm just assuming it is a certain value capital A. And then we are sampling such xt at a frequency 150 pi. So we know by the sampling theorem, we know how to plot the spectrum of the sampled signal. So capital G is right. So you remember in the sampling theorem, we have a scaling of 1 over t. It's right here. Now, previously, when we sketch the sampled spectrum, we always ignore this coefficient. But here, we need to pay attention to that. Okay, so it's the all. So we just follow the standard process to plot all the copies of the spectrum, but now all of them will be scaled by 1 over t. So now 1 over ts is okay, omega s is 150 pi. So 1 over ts is 1 over omega s over 2 pi, which is 75. Okay, so that's why we have this magic number 75 here. So 1 over ts is 75, which means when we plot these copies, all of them will be scaled by 75. So we follow the same procedure. So it's basically, the first copy is the original spectrum, but now it is 75, okay, scaled by 75, between 100 negative pi to 100 pi. And now we are shifting by the sampling frequency, 150 pi. So the second one will be taking this one shift to the right by 150 pi. 150 pi, this one will become 50 pi. And this is 250 pi. No, 150. Not 250. And you have another one here. Okay. So this is capital G. Actually, well, you can see there's an overlapping between these different copies. So once you kind of since they are overlapping means they will superpose with each other, right? So if you draw the resulting, let me use a dark color. The resulting spectrum, once you superpose all these overlapping copies together, the resulting spectrum will be like something like this. Right? And between the overlapping area, the spectrum will be distorted. Right. Now this is because this overlapping area, we have these triangles overlapping with this triangle. So in that region, the spectrum will be distorted. But in the overlapping area, spectrum will be distorted. So we need to find out. But everywhere else, the spectrum will be preserved. So the question is determine the maximum value of omega naught such that within this frequency band, G, capital G equals to 75 of capital X. Well, you can see that 75 is automatically satisfied because once we do sampling, all the spectrum will be scaled by 75 times. So all we need to figure out is a band, a low pass frequency band such that the spectrum of G is not distorted. So if you look at the figure, you can tell that the largest low pass filter band without distortion is this green band, right? Green band. So within this green band, you have this spectrum, which is 75 times the spectrum of X, within the green band. Beyond that, you start to have distortions. So you can see that the maximum band that you can choose is 50 pi. For being out is 50 pi, cutoff frequency. Okay. So which means between negative 50 pi and 50 pi, okay, within this green band, the sampled spectrum is 75 times the original spectrum. Okay, so this is the 7.9. I think that's all of the homework 8. Yeah. So for this type of problems, you just you need to carefully plot the sample spectrums. Okay. Any questions? And we have that exam 2 review. I think you can go over this offline at home. So basically, this will be the examples in the review lecture will be some of them will be similar to the midterm examples. We can quickly go over the. So these are definitions for. We start from Fourier series, right? So this is how you calculate Fourier series for a periodic signal. And for LTI systems, such an complex exponential signal turns out to be an eigen signal of the LTI system. So the response to such a signal is basically a scaled version of the input. And the scaling factor is called the frequency response. And it is given by this integration. So it is related to the system impulse response. And this is how you calculate the Fourier series coefficient. Okay, so I will skip this part. Now in the exam, you need to. It is sufficient to write down the final result in this analytical form. You don't have to figure out the explicit values. But if you obtain some result like this, remember to simplify it into a simpler sine cosine form. And these are the Fourier series properties we have we'll talk about. So I will not go over them here. And we have discrete time Fourier series. And then this is the definition of the Fourier transform. Right, and the properties of Fourier transform, time shifting, frequency shifting. These two are the one of the most important properties. Convolution is another property. We use this one to analyze LTI systems in the frequency domain. So this is the system equation in the frequency domain, and then we can analyze. We can apply Fourier transform to analyze the LTI systems characterized by differential equations, the partial differential equations. So this is an example where we just take Fourier transform on both sides, and then you can identify the system frequency response from this equation. This is how you figure out system impulse response from the system equation. Once you have this, you do a partial fraction expansion and do an inverse Fourier transform to find out the inverse. Okay. So these are the examples that we have gone through in the lecture. And then we have discrete time Fourier transform, which again applies to discrete signals. So you just follow the definition, calculate this infinite summation. Okay, this is a general formula that you can use in the exam if you want to calculate finite summation over geometric series. And again, once you have something like this, try to simplify it into a simpler form. And properties of DTFT, we have almost the same properties. And we can apply DTFT to analyze the difference equations. It's the same idea. Once you have this, you do a partial fraction expansion, and from there you can find out the inverse of the system response. Okay, and then this is lecture 8. We talk about sampling. Now the sampling, all you have to remember is, I think this slides where first of all, you need to know the relation between the spectrum of the sample signal and the spectrum of the original signal. Basically shifting different copies to a proper locations. So the shift is characterized by the sampling frequency. And depending on the sampling frequency and your bandwidth, we may or may not have overlapping between the different copies. And then we have this Nyquist sampling criterion, 2 times the bandwidth. And in the reconstruction phase, we do a low-pass filtering with a proper cutoff frequency. Okay, once we have that, we can do an inverse transform to perfectly recover the original signal. Yeah, I think this, you should be able to plot and visualize the spectrum of the sample signal and then determine the Nyquist rate from there. Okay. So I think that's all I want to say about the midterm exam. So I think for the rest of the time, if you have any questions, I'm free to answer them. Seems there's a construction going on in the upstairs. I don't know why. But I think, okay, so how about this? We end the class here and I will hold office hours starting from 1:30 to 4 o'clock. If you have any questions, come to my Zoom meeting room and we can discuss there. It's a little bit noisy here, so I need to find another place. Okay. So I'll see you guys in the Zoom meeting and see you next week for the midterm exam.
Thank you.
Yep, see you guys.
Is there a practice exam uploaded anywhere?
No, we don't have practice exams, but basically you can redo the homework problems.
Yeah.
And also refer to the review lecture examples. I think those will cover the midterm 2 very well.
Okay, perfect. Thank you.